Today we're going to go over Putnam problem A2 from 2021. Here's the problem. We're trying to find the limit as x goes to infinity of g of x over x, where g of x is itself defined as a limit of this difference. If you remember the limit definition of e, there's a similarity to the limit we see in this problem. So you might expect that e will come up at some point. Feel free to pause the video and try the problem yourself. Moving on, we can go further than our vague statement that e should show up somewhere by noticing that using a linear approximation for the derivative of x to the r plus 1, g of x is approximately equal to x times e. This isn't exact, but because the limit we actually want to find involves dividing by x and letting x go to infinity, that error is going to become insignificant, and g of x over x is going to be roughly e. This whole argument is based on the trick, if you want to call it that, of taking a difference and approximating it using derivatives, and seeing if you can make progress with that approximation. You could use this argument to get a proof that the solution to our problem is indeed e, but I want to show you a different argument now. This argument involves recognizing an integral hidden in the definition of g of x. By the fundamental theorem of calculus, the integral from x to x plus 1 of r plus 1 times w to the r dw equals x plus 1 to the r plus 1 minus x to the r plus 1. This is a useful symbolic manipulation to remember. We can now rewrite g of x as follows. We can also pull the constant r plus 1 out of the integral. What do you notice in this new expression? Well, using the product rule for limits, we see that we can pull an e out of the expression to get the following for g of x. With this new expression for g, let's go back to what our problem is really asking us to do. We want to find the limit as x goes to infinity of g of x over x. Our intuitive argument earlier tells us that we want this to equal e. We know it's currently a product of e and something else, so we want that something else to have a limit of 1. One thing to notice about the integral and the limit is that the integrand is monotonic. When you have a monotonic integrand, you can bound your integral by plugging in the limits of integration to the integrand, which is something we can try here. This is starting to look interesting. If we take the 1 over r power, keeping in mind that when r is negative we had to invert the inequalities, we get in both the case r greater than 0 and r less than 0 that the integral to the 1 over r power is between x and x plus 1. Since x is independent of the limit variable r in the definition of g, this means that g of x is between e times x and e times x plus 1, which means g of x over x is between e and e times x plus 1 over x. Now we can take the limit as x goes to infinity of our bounds for g of x, which converge to e, and apply the squeeze theorem to get our result. To summarize, we first used our intuition to say that e should be involved, and further that our answer should be e. Then we recognized an integral with monotonic integrand, which is especially nice because we can bound it, which is useful because we're ultimately trying to find a limit, and bounding lets us apply the squeeze theorem. That's all for this video. Thanks for watching.